So we're looking today at Year 2, Chapter 9, of A-Level Maths, Differentiation. So there's a few things that we need to go through. Let's have a look at think about what we are going to be doing. So in Year 1, we looked at differentiation, but we only looked at things which are really in the term of a plus x and x to the n. So we were looking at things which were like this. Y is equal to 3x to the power of 4, and we know that that differentiates to 12x to the power of 3. Okay, we times the power by the front and then take away 1. However, people get caught up on that. People get really caught up on that, and they think that they can just, it's all about the powers. And differentiation isn't about the powers. Differentiation is about finding the gradient of your curve. This is called the gradient function, okay? And you're finding the gradient of your curve at a particular point, and that's what this does, okay? This is our curve. And the thing that's on the right-hand side is how we find a gradient at a particular point, okay? So we're going to be looking at how we find the gradient at a particular point, but for different functions now, the new functions that we've been looking at. So, for example, trigonometric, exponential, and log. We're also going to be then looking at new rules to find out differentiation, which is called the chain rule, the product rule, and the quotient rule. We're then going to be looking at differentiating parametric equations. We then look at implicit differentiation, which is differentiating things that aren't in the order y is equal to something, something, something. And then we're going to look at rates of change, which is kind of more the problem-solving kind of things, when we start to use differentiation a little bit more. Okay, so the first thing that I want us to have a little look at is this one here. Now, I am actually going to put a little note in this, because I think it's always worth trying to understand it before we think about the proof. Okay, so you can write it on side title if you want, which is differentiating trigonometric functions. If you want to write that down. Okay, so I'm going to think about what the graph of sine x looks like, and the graph of sine x looks like this. We know that it's a repeating pattern, and it goes like this. So we know that the peak here is at 1. We've got a minimum over here at -1. And if I'll do it in terms of radians, just because, so this is pi, this is 2 pi, like so. Now remember what I said to you. Differentiation is about finding the gradient at a particular point. Now I'm just going to tell you a little piece of information here. I'm going to tell you that the gradient, when we cross the gradient, when we cross the x-axis is equal to 1. Okay, I'm going to tell you that. Now, the reason I'm telling you that is because we could prove that if we want to, we could go on dead maths, but I'm just going to tell you that for now. Okay, so what we're looking at here is we're looking at what is the gradient at particular points. So we know this is our sine graph. Y is equal to sine of x, like so. Now I'm telling you that here, this gradient here, m, is equal to 1. And at this point here, what is the gradient at this point here? Well, at this point here, we can see that it's a flat line, so my gradient of this one must be equal to 0. Now, actually, I should say plus or minus 1, actually. So the gradient at this point here is -1. The gradient at this point here is equal to 0. We can see that. And the gradient at this point here, we know it's a repeating pattern, so that must be the same as the starting one. These two here, so this one and this one should be parallel because they're exactly the same. And we know that the gradient at this point here is equal to 1. Now you might think to yourself, well, why are you doing this, Mr. Adams? What's the point in this? I'm going to show you the reason now. I'm just going to take this actually, move it down slightly, make it a little bit bigger just so you can see it. And then directly underneath this, I'm going to draw so another axis. Here's my axis like so. And I'm going to go literally straight down here like this. So this is pi. This one here is 2 pi. And I'm going to plot the gradient function. Okay, so what did I say my gradient was at this first part here at 0? Well, I can see here my gradient, which is this line here, is equal to 1. So I'm going to plot that. Here it is. So my first one is 1. Then when we're at this point here, I think I put the gradient is 1 at this point. It's not 1. The gradient at this point here is 0. So in fact, I'll probably do it in a different colour. So here's my first one, 1. The gradient at pi over 2 is 0, so let's plot that 0. The gradient at pi is equal to minus 1, so let's plot that minus 1. The gradient at 4 pi over 3 is, well, at this point here, look, my gradient there is equal to 0 again, because it's a flat line there. So my gradient here is 0, and at 2 pi, we're going back to 1, which is there. So what do we spot about this? Why have I done this? What is the gradient function? If I plot all the gradients of sine, what do I get? What graph is this? It's the cos graph. Yeah, that's exactly what it is. Yeah, this here is my sine graph on the top. And if I plot this, dy by dx, which is my gradient function, this here is my cos graph. So this here is cos of x. And that's what I want you to think about. I don't want you to think about now times in the power and taking away 1. You're thinking about, when I'm differentiating, what is my gradient function? Okay? And that's why I always draw that. I think it's always worth drawing something like that. Now, there is a proof for this. Okay? And you can get tested on this. So I'm just going to go through this proof. We're going to do it from first principles. So the first thing I'm going to say is let y be equal to sine of x. I'll be honest, I don't see this come up very often, but they have said that you can get tested on it, so it's definitely something that we need to do. In fact, I probably should have actually said that this is equal to f of x, because we're doing it from first principles. So y is equal to f of x, which is equal to sine of x, like so. And if we're doing it with f of x, we know that dy by dx is equal to f of x plus h, so that tiny bit over, remember, minus f of x all over h, but knowing that this is the limitation that h tends to 0. Like so. Okay, so let's sub in what we know now. So we know what f of x is. We're going to need to know what f of x plus h is. So f of x plus h is equal to, well, it's just going to be sine of x plus h. So limitation of h tending to 0 of dy by dx. Oops, I've done this wrong, haven't I? Silly Billy. That needs to go. Something there. So we're going to say that dy by dx is equal to the limitation that h tends towards 0. And we know that f of x plus h is equal to this sine of x plus h minus sine of x all over h. Now, I am going to make this bigger because I want to see some more space here. So let's do it down here. Let's take this. Let's take all of this. I'm going to do it down here. So, I'm going to need some more space here. Now, the problem we've got is this part here, okay? And with this part here, we need to split it up. So to split it up, we're going to use our double angular formulas, which is sine of A plus B is equal to sine of A cos of B plus cos of A sine of B. We know that. Okay, so if I want to split this part up here, I'm going to have dy by dx is equal to the limitation that h tends towards 0 of sine of x cos of h plus cos of x sine of h minus the sine of x all over h. Okay, it's getting a bit trickier now. So the next thing we need to do is collect our collect all of our signs together. So it's going to be dy by dx is equal to the lim of x tending towards 0. So let's bring the sine x's together. So it's going to be sine of x times by. Now, in fact, I'm going to draw them first just so you can see what I'm talking about. So cos of h minus the sine of x plus cos of x sine of h all over h. So I've just moved that sign there so I can take out the sign as a common factor. So this is equal to lim of h tending towards 0 sine of x times by cos of h minus 1 all over h of the plus. Now I'm going to split these two up because I'm going to deal with both of these separately, okay? Cos of x sine of h all over h there. Okay, super. Now, there's a part which you're going to need to know, and a part that you're going to need to show. And this is using small angle approximation. Now, we have done this before. We know that since lim of h0 of sine of h is approximately h. We know that from small angle approximation. Therefore, the limitation of h tending towards 0 for, now I'm just going to deal with this part here, okay? So sine of h over h means that we get h over h. I'm going to need to... So the limitation of h tending towards 0 of h over h, which is equal to h divided by h, which is 1. So we know that this yellow part here is equal to 1. We're now going to deal with this part here. And we already know, again, from small angle approximation, so the limitation of h tending towards 0 gives me cos of h is approximately, we know that cos of h is approximately, let's check it, 1 minus a half h squared. We know that. Okay. So therefore, the limitation of h tending towards 0 of this blue part here, which is cos of h minus 1 all over h, is equal to limitation of h tending towards 0 of 1 minus a half h squared, because that's what this is over here. We know that cos is that, minus 1 all over h there. So then these are all going to cancel. So we end up with, the 1 and the 1 will cancel. We end up with minus a half h. So this is equal to lim of h tending towards 0 is equal to minus a half h. And obviously if h is tending towards 0, then this is equal to 0. Okay, we're getting there now. So out of all of that, we know that the blue part here, let me just highlight this. This blue part here, which is the blue part there, is equal to 0. We know that the yellow part there is equal to 1. So we're just finishing up now. So we can say that this is the limitation of h tending towards 0 is equal to sine of x times by, from small angle approximation, 0, plus cos of x, and from sine angle approximation, we know that's times by 1, which is the yellow part. So therefore, we've finished up because we know that this is going to be equal to 0, so that will cancel. This is just going to be equal to cos x. So I end up with dy by dx is equal to cos of x. There we go. Nasty that is. Loads going on there. Now, that looks really nasty, and it is. I wouldn't overly worry about that. I have to go through it with you because it can come up. However, I haven't seen it come up, and it doesn't come up very often. However, they can ask it. It's definitely worth knowing. You do need to know it. And it's just about thinking about small angle approximation. You're using two things, aren't you? You're using the addition formula for, so sine of a plus b, using over here. That's important. And then the other part is just the sine angle approximation. If you know those two, you can kind of get through this proof relatively easily. Can I just have a show of hands who's all right with that? Good, good, good. Okay, so let's have a go at our next part then. So we've done that now. We know this. There's the proof. They've done it a little bit shorter than I have. But we know that differentiating sine x gives us cos x. That's our starting point. And we're doing this from small angle approximation, which is this part up here. So we've done that now. Now, this is definitely worth noting that this only works when we're in radians, and the reason it works is when we're in radians is because we're saying that y of sine x is approximately 1. So we're saying that sine of x is approximately x when we have something that's really small, and this only works with radians. If you look here, it doesn't work there with degrees. It only works when we're in radians. Okay. So they talked about a little bit here. Now I always think about this. This is the way that I remember the cos, and I do this one here. C. No. So this is how we remember differentiation of sine and cos. So it goes S C minus S minus C. And if we're differentiating, then we're going around this way. And if we're integrating, then we're going this way. And you will need to know the integration. So what I'm saying here is that if I differentiate sine, then the answer is cos. So let's just show that. If I've got y is equal to sine of x, then dy by dx is equal to cos of x. And in the same way, let me just get rid of these ones. Oops. So if I'm differentiating cos, let me do this in a different one. So f of x is equal to cos of x, then f dash of x is equal to, so if I'm differentiating cos, f dash of x is equal to minus sine. If I'm differentiating minus sine, it's equal to sine. If I'm differentiating minus sine, it's equal to minus cos. If I'm differentiating minus cos, it's equal to sine. Can you just pop your hand up if that makes sense and you understand that, what I've done there? So if I'm differentiating, we're going around this way, just a way of remembering it. And if I'm integrating, I'm going the other way. Super. Pop your hands down for me. So we've got one more little part. Now this actually comes from something that we're going to do in a little second, which is called the chain rule. Actually even says that there, doesn't it? We'll talk about this a little bit later. But we know that if I'm differentiating sine, the answer to sine k of x, now k is just a constant, is going to be equal to k cos of kx. We times by the number in front of it. We'll talk about why that is in a second, but don't worry too much about that for now. If I'm differentiating cos, I know that cos goes to minus sine, so in which case this is going to be equal to minus k sine of kx. You need to know these. There's going to be loads of things you need to know how to differentiate. So I'm going to do a couple of these, and then I'm going to ask you to have a go at some yourself. Maybe I'll even pick a couple. So I'll do this first one here. So if I'm differentiating sine of 3x, this is equal to 3 cos of 3x. Nice and easy. Yeah, I'll do this one down here as well. If I'm differentiating this one, no, I won't do this one. I'll do this one on the right over here. So if I'm differentiating this one here is going to be, well, you times the 3 by the 4, which is going to be 12. Cos differentiates to minus sine, so it's going to be minus sine times by 3x. Minus sine of 3x, sorry. So you do whatever's in here inside your function times by what's outside, the differential of that times by what's outside your function. We know that cos differentiates to minus sine, so it's going to have to be minus 12, and then whatever's in that bracket stays the same. Okay, have a little go at those 4 underneath, and then I'm going to put the answers up in a second. Have a little go at those 4 underneath. Okay, I'm going to give you another 20 seconds and then I'm going to go through them. Yeah, spot on. So it needs to be, yeah, cos differentiates to -5. But I also know from the chain rule, which we'll talk about in a second, the 5 needs to go in front. So this is going to be equal to minus 5 sine of 5x. I'll do one of these harder ones. I'll do this one here. So this one here. With this one on the bottom right, you can see that actually, because although you've got the coefficient, you've also got minus cos there. It's minus cos of a half x. Well, minus cos differentiates to positive sine. Now, you could, if you wanted to, think about the minus, but don't worry too much about that. So it's going to be 2/3 times by 2/3 times by a half of positive sine half x, and they will cancel, so I end up with just a positive 1/3 sine of a half x. Now we'll talk about this a little bit more later when we're doing the change rule. Here's those answers to those if you want to go mark them now. So mark those ones at the bottom. Okay, let's have a look at this one then. So this is from the textbook. A curve has an equation y is equal to a half x minus cos 2x. Find the stationary points of the curve between the interval of 0 and pi. Now remember, first thing you're thinking here is stationary points. What does stationary points mean? Well, stationary points means that when dy by dx is equal to 0. That's what we're trying to find. So here, the first thing I'm thinking is dy by dx is equal to 0. That is when our stationary point is. Okay, so I'm going to do that by differentiating. So let's differentiate this now. Now I know how to differentiate this from last time. To differentiate a half x is just going to be equal to a half. And we've just learned how to differentiate these parts here. So I'll write down what the equation is. Y is equal to a half x minus cos of 2x. Differentiate the first part, dy by dx is equal to is equal to a half, cos of 2x. So if I differentiate this, I end up with dy by dx is equal to, if I differentiate the first one, well, we know that if we differentiate something like 2x or 3x, we know it's going to be equal to 2 or 3. In this case, it's going to be equal to the half. If I'm differentiating minus cos, well, thinking about that little sine, cos, minus sine, minus cos. Minus cos differentiates this way round clockwise to sine. So it's going to be plus 2 sine of 2x. You know that. So now, because we're asking to find the stationary points, we're going to find when, so stationary point when dy by dx is equal to 0. So we're going to set this equal to 0. 0 is equal to a half plus 2 sine of 2x. Let's take that half over. So we're going to end up with minus a half is equal to 2 sine of 2x. Divide by 2. I'm going to take the sine over to the other side as well. So sine of 2x is equal to minus a quarter. So we're going to have to use our cast diagram now. So we can say that my acute 2x is equal to sine to the minus 1 of a positive quarter. So remember, I'm trying to find the acute angle for this. So shift sine to the minus 1 of 0.25. I'm going to need it in radians, aren't I? So shift setup, radians. So shift sine to the minus 1 of 0.25, which is equal to 0.25 there. Just going to check that. So my acute 2x is equal to 0.25 3 it is to 3 decimal places. So then I'm going to draw my cast diagram, C, A, S, and T. So because I am negative a quarter, I know that I'm going to need to be in, and it's sine, tan, and cos. And it's going to be this part here is equal to the 0.253. This part here is equal to the 0.253. This is pi, this is 0 and 2 pi. So it's going to be 2x is equal to pi plus the 0.253. So shift pi plus 0.253, which is equal to 3.3. It's actually 3.40 to 2 decimal places. 3.40. I should do it to 3 actually. 3.395 it is, but also it's going to be this one over here, which is 2 pi minus that. So 2 shift pi minus 0.253, which is going to be equal to 6.030. Now, you do need to think about your interval here because I'm dealing with 2x, so my interval actually needs to be 0 is less than or equal to 2x is less than or equal to 2 pi, and I've got that between 0 and 2 pi. So my last little stage here is to divide both of these by 2. So divided by 2, this one on the right is going to be 3.02 to 2 decimal places, radians. And this one on the left-hand side, 3.395 divided by 2 is equal to 1.70 radians to 2 decimal places. Let's just check that. I thought I'd made a mistake there. No, I haven't. This is right. So I still haven't actually finished here because I've only found out what x is, and it's not asking for what x is, have they? They're asking for what my stationary point is. Okay, so we're right in saying these two here are right. These are the x coordinates, but because they're asking for the points, now just need to be careful. Is this over? No, we are right. So yeah, we've got our x coordinates, but we also need to find our y coordinates. I'm going to do that by subbing them back into this top bit up here. So let's maybe split this up a little bit, just take it over very slightly. So our first one is going to be equal to y is equal to a half of 1.70 minus cos of 2 times by 1.70, which in this case is equal to y is equal to 1.8, 1.82, and for this one here exactly the same, y is equal to a half of 1.70 minus cos of 2 times by, it should be 1.70, should it? It should be 3.20, silly Billy. 3.02 times by 2 times by 3.02. So y is in this one is equal to 0.54 to 2 decimal places. So our two stationary points here are 1.70, 1.82, and the other one is equal to 3.02 and 0.54. There, so there's our two stationary points. So a lot going on there. It's kind of straight in with it, isn't it? Can you just pop your hand up if you're happy with that? You all right with that there? Good. Good, good, good. Perfect. Super. So they've done it to 3 decimal places. I've done it to 2 decimal places. That's fine though. All right. Have a little go at this one yourself. Okay, have a little go at this one yourself. I'll give you a couple of minutes or so, and then I'm going to go through it. So have a little go at this one here. Okay, I can see that some of you are starting to finish, so I'm going to start it just so we can have a little go at it. So we can crack on. So a curve has an equation, y is equal to sine of 3x plus 2x. Find the stationary point of the curve in the interval 0 and 2 over 3 pi. Okay, so first of all, I'm going to need to differentiate this. So it's going to be dy by dx is equal to 3 cos of 3x plus 2. If I'm trying to find my stationary point, I know my stationary point is when dy by dx is equal to 0. Let's just state that. Is when dy by dx is equal to 0. So we're going to say that this is equal to 0. So 0 is equal to 3 cos of 3x plus 2. Take the 2 over, divide by the 3, and end up with cos of 3x is equal to minus 2 over 3. Let's find the acute angle. So my acute 3x is equal to cos to the minus 1 of a positive 2 over 3 in radians, don't forget. So shift cos to the minus 1 of 2 over 3 is my acute 3x is equal to 0.841. Draw my cast diagram. CAST, remember the negative, the important part, because that tells me where I am. And so because I'm negative, I know that I'm going to be in sine and in tan because I'm dealing with cos. So this angle here is equal to 0.841. This angle here is 0.841. This is pi. This is 0 and 2 pi. So in which case 3x is going to be equal to pi minus 0.841 and pi plus 0.841. So let's do both of those. Shift pi minus 0.841. So 3x is equal to 2.301 and plus this is equal to 3.983. So divide both of these by 3. So x is equal to, remember, you're leaving that dividend until last. So 2.301 divided by 3 is equal to 0.767. And this one here is equal to 3.983 divided by 3 is equal to 1.328. Now I do need to be careful again of my limits and boundaries because I need them to be between 0 and 2 pi over 3. I'm going to just write it as a decimal so I can see what it is. So 0 is less than or equal to x is less than or equal to, what is 2 over 3 shift pi? Let's do write it as a decimal so I can see it. 2.09. So there is a chance there's a third one here. If I think about this one here, let's just check it. 2.301 plus 2 shift pi is equal to 8.5 here. And what's 8.58 divided by 3? No, that one's going to be outside the range, so we don't need to worry about that one. So we do have 2 here which are inside my range. I'm still not finished because I just need to write down what the y values are. I'm going to do that just by subbing them in. So I end up with x is equal to 0.767 when y is equal to 2.2 7, 9. So there's my first coordinate. And the next one, x is equal to 1.328 when y is equal to 1.910. Brilliant. You just pop your hand up if you're happy with that. Super. Okay, so we're just going to take it to our next stage now. So we've looked at differentiating sine and cos, and we know how to differentiate those. The next thing we're going to be looking at is differentiating exponentials and logs. Okay, and I think you've already had a little look at this, haven't you? You've already had a little look at differentiating this one. I'm sure you know this first one. No, differentiating e to the x is e to the x. We know that. And that's because if I take the gradient of any point on the e to the x graph, the gradient of that point is the same as the x coordinate. Okay. We also know how to differentiate this one. This one here is going to be k cos of kx. We know that one. Now this one here is a new one. Differentiating ln x. Now this differentiates to 1 over x. There is a proof of that. I'm not going to do that one just now. They've also done this up for here. So they've said that if I differentiate this here, you end up with, using the laws of logs, you end up with a value plus ln of x. We know that if we differentiate, let's say, because this is just a number, so this would just be 2. So if I was to differentiate 2, we know it's just equal to 0. So if we differentiate, it's worth saying underneath here as well, probably. So if we differentiate ln of kx, this is also equal to 1 over x. That's what they're saying over there. This next one is new. Now, again, there is a proof of this. I can go through that proof. I'm not going to do it right now. If I differentiate a to the x is equal to a to the x times by ln a. And a to the kx is differentiates to a to the kx ln of ka. Oh, sorry, no, it's not. K of ln a. Now you will need to know all of these, and to be honest, there's a million of these you need to know. A lot of them, some of them are in our formula book, some of them aren't in our formula book, but you will need to know all of them. You'll need to know them off by heart, because if you don't, then you struggle to kind of know what you're doing with these. You really need to have a strong understanding of every single one of these. And this last two, sorry. Okay, super. So we got those ones there. There they all are. So let's start having a go at some of these. Now, you can use these notes to help you. In fact, I'd probably suggest using the notes to help you. So the first one here, differentiate 3 to the x. Now, using the formula, we're going to be using 3 to the x means a to the x, which is going to be this one here. So if I'm differentiating that one there, it's going to be equal to 3 to the x ln of 3. Same here, a to the x ln of a. Differentiating x cubed. Now, they've put that in there to do it a little tricky. This is one of our older ones, isn't it? This one here, you times the front by the power and then take away 1 from, sorry, you times by the power and take away 1 from the power. this one here is going to be equal to 3x squared. This next one here, when I'm differentiating ln x, let's just have a little check. What's ln x when I differentiate it? Well, that's just equal to 1x. What about ln of kx? Well, that's just equal to 1 over x as well here. So ln of 3x, which is what we've got, is just equal to 1 over x. If I'm differentiating this one here, 3 to the 2x, that's going to be equal to, what did we say this was? It's going to be 3 to the 2x staying the same. Then it's going to be equal to 2 ln of 3. Just check that. Yeah, good. They put that in brackets. It's probably worth putting that in brackets just so you know. Now that comes from this one here. So I've done a couple there. I've done a few there, sorry. Have a go at the rest of these yourself. Have a little go at those ones yourself. Everybody else. So it's from this one here, isn't it? I'll just do this one on the side. I did this one pretty quickly. So 1 over, it's from this one here. So the question was, why is 1 over, why is the ln of 3x only equal to 1 over 3x? Now the reason for that is because of our laws of logs. I'm just going to do on the side over here. Now, you can just remember if you want, like so, like this. However, we know that if I'm differentiating ln of 3x, from our laws of logs, we know that we can split this up. So we know that we're differentiating ln of 3 plus ln of x. Now, ln of 3 is just a number. So if I was differentiating the number 2, well, I know that number 2 is just a flat line like this, isn't it? Which my gradient of that is equal to 0. If I'm differentiating a number, my gradient is 0. So this here, just thinking about this, there's 2. A gradient that is equal to 0. If I'm differentiating ln of 3, that is also equal to 0. So the only one I'm really differentiating is this ln x, which is equal to 1 over x. Okay, so have a go at the rest of these then. So I'm just going to go through this last question. I'm going to put the rest of the answers up, just put them up. So this last one here says the rabbit population after t years can be modelled using p is equal to 1000 t 2 to the t. Determine after how many years the rate of the population will have increased, so will have reached 20,000 rabbits per year. Now the thing we need to think about here is the fact that it says the rate of the population increase. Okay, determine the rate of the population increase. So with this one, we're saying that P is equal to 1,000, 2 to the T. Now, when we're differentiating this one, you just differentiate inside of here. So this is going to be dp by dt is equal to 1,000 times by 2 to the t ln of 2. So that one there. And what we're saying here is, when is this equal to 20,000? So we're setting this equal to 20,000. So 20,000 is equal to 1,000, 2 to the t, ln of t, ln of 2. So to get the 2t on the own, I'm going to need to divide both sides by 1,000 to ln 2. So 20,000, in fact I'll do it on my calculator, whoops. $20,000 divided by 1,000 ln of 2 is equal to 20 ln 2. What was it? 20 over ln 2. So t to the 2 to the t is equal to, oh, what was it? I forgot what it is now. I'm sure it was 20 over ln 2. 20 over ln of 2. And then the last little part, I'm going to need to go, so t is equal to log base 2 of 20 over ln 2, whatever that is. Let's do it on my calculator. So, log base 2 of 20 over ln 2, close the bracket, gives you something nasty. Let's write it as a decimal, which is 4.8 years, 4.85 years. Just going to check the answer. Get away. No. Yeah, 4.85, brilliant. 4.85. So I've done that one there. There's the rest of them. So mark those ones you've done. Mark the ones you've done. Super. Now we've got to test your understanding here. We've got a few questions to have a go at. So take 5 minutes to have a go at take five minutes to have a go at those two. And then I'll have a go at some of these, okay? So take a few minutes, just have a go at both of those. They've given you a little hint there to expand that first. So what they're saying here is that I'll probably do it over here. So we know we're going to do x, e to the x times by 2, times by e to the x times by 2. So what is that? E to the x times e to the x is going to be, when you add the powers, so it's going to be e to the 2x. There you go. 2e to the x, 2e to the x. I'm helping you out here too much, probably. So y is equal to 2x. That's your starting point for that one. Pop your hand up if you finish both of those. I'm going to start going through them so you can have a little check. So if I'm differentiating this first one here, so dy by dx, you just got to know how to do all of these. I think that first part is probably the hardest part, just having to differentiate all of these. So it's going to be 2e to the 2x plus, no, that just stays the same, 4e to the x. And the 4 differentiates to 0, so that just stays the same. So there's that one there. First one's nice and straightforward. It's just about knowing that chain rule part. And you will get used to these. The more you see them, the easier they become. This next one's probably the harder one. So, the child has head lice and his parents are treating it using a special shampoo. The population of head lice can be used modelling to use, this is our model here. Determine how many days it would elapse before the child has 20 head lice left. So, we're trying to find the time in days after the when the population is only 20 head lice. So we're not trying to find the rate here, we're just trying to find out what our time is, knowing that the population is 20. So we're going to say that P is equal to 20. We're subbing that into this formula, which is P is equal to 460 times by 3 to the minus 2t. So 20 is equal to 460 times by 3 to the minus 2t. Divide by that 460. Hey. So it's going to be 20 divided by 460, which is equal to 0.0435 is equal to 3 to the minus 2t. So change this using our laws of logs. Minus 2t is equal to log base. Put ln 3. It needs to be log base 3 of 0.0435. And then divide by that negative 2. So t is equal to, let's type it all in. So fraction button first. Log base 3 of 0.0435 all over minus 2 is t is equal to 1.43 days. 1.43 days. Brilliant. So the next part says, determine the rate of change of the headlights after 3 days. So that was part A. Part B is the rate of change now. That's really important. Because it's not the population, it's the rate of change of the population, which is dp by dt is equal to, now I need to differentiate this. This is the hard part. 460 times by, well, this is going to stay the same. It's going to be 3 to the minus 2t times by the minus 2t. So times by minus 2t. ln of, sorry, I forgot that. ln of 3. So then if I want it when t is equal to 20, I need to sub 20 in this to this and find it out. So dp by dt is equal to 460 times by 3 to the minus 2t times by 3 times by minus 2 times by ln of 3. So let's type all of that into my calculator. So 460 times by 3 to the power of negative 2 times by 3. Right button, close that bracket. Times by negative 2 times by ln of 3. So the rate of decrease, I'm just going to check that before I write it. Yeah, it's right. So the rate of decrease in this case would be equal to dp by dt is equal to minus 1.39, and that would be lives per day, isn't it? It's the population, isn't it? It's lives per day. There you go. There's that question done. So we're going to pause there for a bit. We will come back to